Hello world, and welcome to this session on Geopandas, about producing maps and handling geographic information in Python using this package Geopandas. So in our group we tend to use two different systems for doing geographical work. One is QGIS and the other is Geopandas, and both are great. They're just a little bit different and have their different strengths and weaknesses. QGIS is probably the best system to use if you want to really kind of explore, be zooming around, be sort of selecting individual areas to see what data is associated with those, so a more interactive environment. And Geopandas is probably better for large-scale manipulation of geographic data, sort of matching up geography to other data that you have, and then producing high quality maps, sort of publication or for reports. And you can also automate it very easily, so you can produce a whole different series of maps under different scenarios. So they're both great, but today we're going to focus on Geopandas. Right, before we get on to Geopandas, we're just going to talk very quickly about coordinate reference systems, CRS, and projections, because they can be one of the most fiddly things, whether you're working in QGIS or Geopandas. Is what coordinate reference system is your data using, and is it appropriate for what you're trying to do, and does it match other data, geographic data that you've got? We tend to use just a couple of different ones, which I'll mention. But right, the CRS is a way of referencing any point on the globe. Now there are global systems such as WSG84, and there are notes of what these are in the Jupyter book, and that is used, for example, by GPSs and to highlight any point on a globe. And it takes into effect that, because this globe is sphere, the real world is actually slightly flattened. The equator has been sort of spun out a little bit by its rotation, and that sort of brings the north and south poles just slightly closer together. Things like WSG 84 take that into account. And you can point to any place on the Earth with a latitude and longitude, which is the coordinate reference system that goes along with using a globe type system. So that's all very well if you've got a globe and you can sort of find latitude and longitude and everything's a nice simple system. What if you want to produce a flat map? Or maybe you want higher accuracy, because the world not only is slightly flattened, but is also a bit more bumpy and uneven, and so local coordinate reference systems that we'll look at take more account into those sort of inaccuracies of the globe the world not being perfectly spherical, or even sort of flattened sphere. So there are various ways of doing it. I think, most fun way, I think, is that there's something called the azimuthal equidistance, and you measure the distance and angle of everywhere from the North Pole. So I can come down here, and if I want to go all the way down to the South Pole, that's as far as I can get, and it's also in every direction. Everywhere south from the North Pole ends up. So that's where we get the sort of iconic flat Earth map, really. But it is a genuine projection as well. So here's the North Pole. Here are the continental land masses, and all around the outside is the South Pole. And it's actually the map that the United Nations use as well, though they take away the South Pole, they just use the continental masses. So that's one, and that's a genuine projection that you can use. I've mentioned this is the WGS84, and you can see here there's a wiki page about it, and it has a flattened, this is exaggerated here, it's a flattened sphere. The other one, now we tend to use either data that's lat long data in WGS84 or the British National Grid. This is the Ordnance Survey grid, and this just takes a small area of the Earth around the United Kingdom, and it transforms it to distance in meters from a particular reference point here, which is the sort of you'd go as far west as you can in the United Kingdom, as far south, and that's our 0, 0 point. And then we get northings in meters away from that point, and we get eastings in meters away from that point. So the British National Grid works normally on eastings and northings from a reference point. So you might have data that's WGS84, that's one of the most common ways of receiving geographical data with the lat long, or you might have it already in the British National Grid. You'll see it's got, so its full name here, OSGB 1936, British National Grid, and all of these, or nearly all of these coordinate reference systems have what's called an EPSG code, and that's the European Petroleum Survey Group, and they took responsibility for collecting all the different coordinate reference systems and projections that are used by people. So anything substantial, I mean, you can make up your own coordinate reference system, but anything that's commonly used at all will have an EPSG code, and that can be important when you're trying to find the projection you want and the CRS you want, either in QGIS or in Geopandas. Okay, that's just an introduction to projections and coordinate reference systems. Okay, so our first task is to set up a Python environment to do this work in. As ever, it's good practice to have an environment for a particular type of task or for a project, and that stops conflicts between different Python versions or different package versions that different jobs might need. So in the video description below, there's a link to the GitHub repository where all of this is to be found, and I'm going to copy that, so you can download the zip if you want. If you've done anything with GitHub before, then you'll know it's much more convenient to use git clone, but if you're not familiar with that, just download the zip and unzip it. So I'm going to git clone that. Okay, I paused that just while it was doing it. It took about 30 seconds to download. There's a fair amount of data that brings down for this demo, and also some images. Okay, so I'm going to move into that directory. So if you're using Windows at this point, well, in fact, from the git clone point, you want to be using Anaconda prompt. I think that's what they call it, which gives you a terminal like this, or a console they might call it. Now, I'm now in that GitHub repository that I've cloned down, and if I just look at the directories, I can see we've got binder, Geopandas 1, which is notebook, images, readme. So it's the same structure as you can see here. Now the environment here is in a folder called binder, and the reason that the environment, or the environment file that's going to help us set up the environment, the reason it's called binder is you can click on this down here, launch binder, and that sets it up on the web. Though be warned, it's slow to start if it hasn't been used for some time, because it's got quite a complex image to build up. But that's why it's in there. If we look, I'm just going to look in here and let's see what the environment file looks like. These are YAML files, yet another markup language. So if I click on an environment YAML file, what we can see is they're fairly simple and nice and easy to construct. And here I've got the name that it's got, the environment it's going to create. It's called Geopandas. Channels defaults is Conda, Anaconda package manager. Conda Forge is the community package manager. So sometimes it can't find things in the main Anaconda package manager, and it'll go down and look next in Conda Forge. If you switch those around, it will look at Conda Forge first. And then we have what we want to install. Now here I've given version numbers. That makes it faster to set up. It also means you should end up with exactly the same environment that I've got. So we can see Geopandas equals 0.9.0. You can just give it partial. You can say equals 0.9 and then it will find the latest 0.9 that it can. So here it looks like it's 0.9.0. And then we tell it also usefully which Python version. So all this is going to run on Python 3.8. And then pip. So some things aren't in Conda or CondaForge, we can also put in please pip install. And here I've got this, I find it very hard to pronounce, contextually. So it's going to Conda install all of those, and then it's going to, once it's done that, pip install contextually. So I'm going to move to where that environment file is with cd for change directory into binder, and then I can see environment no versions is just a way, if you wanted to sort of see, well, what's it going to come up with now if it goes out and looks for the latest compatible versions of everything, and it might load up, for example, Python 3.9 or later if you're watching this after 3.10 or more are released. So environment no versions, if I just look at that, it's exactly the same, but it just doesn't give the version numbers. We're going to use the version number 1 here. So to create from if somebody's given you an environment file, that's the best way to set up an environment, because particularly if it's got version numbers, it means you reproduce the environment they're working in. So it should work. So conda env create from file, and I can tab complete. It's gone to environment. There are actually 2 environment files because there's the no versions, but if I put a dot and tab complete there, it knows it's got to pick up the environment and not the environment no versions. And I'm going to run that. I'm going to pause it while it does that. Geopandas can take a little while to install. Okay, that took probably about 2 to 3 minutes to install. So it's sort of said now to use this environment we conda activate Geopandas. Let's just have a quick, if you want to sort of see what environments you've got installed, and if you've got Anaconda, it always installs one called base, conda env list, and we can see the environments. Some of them hidden behind me, it looks like that, but you know, you get the point. These are the environments I've got running on my computer that I switch between depending on the work that I'm doing. Okay, now I'm in the binder directory. I'm just going to go up one with cd double dot and back up to Geopandas. So I'm going to activate the environment from here, and then I'm going to launch the Jupyter notebook. So conda activate Geopandas. Conda, yes, I did. Activate Geopandas. And then if we do conda list, we see all the packages that are installed in the environment that I'm in at the moment. So we should see Geopandas in here somewhere. So we obviously got a lot here. These are all the dependencies. It automatically installs Geopandas, and this is version 0.9.0. So that's good. That's what my environment file said to import. So now if I launch Jupyter Lab, shut these down. Now I'm in Jupyter Lab, look at what's in my folders, and here I am in the right place. I've got Geopandas 1 and Geopandas 2. So we're just going to go through Geopandas 1 today. I'll quickly show you at the end what's in Geopandas 2. It's just a couple of extra, well, it's how to embed a map within another map if you want to sort of put the Isles of Scilly, for example, in close to a Cornwall map. Okay. Okay, let's get on to Geopandas itself then. We've installed the environment. So at the top there's just a list of what we're going to go through. We've done installation. We're going to load up a standard geography file, the sort of stuff, well, we'll go and find out where you get them from the government, that they're called shape files, which have all the different kind of regions in. We'll set the coordinate reference system for that, and we'll create a map, and then we'll merge some areas. That's the sort of handy thing you can do in things like Geopandas. And then we'll also look at selecting a small area from within a larger area. We'll add some points rather than areas. We'll convert between British National Grid and lat long. And then we'll look at how you can produce some very nice looking maps using matplotlib. For this, I'm going to assume you have covered the basics of pandas, because Geopandas behaves just like pandas, which is the nice thing, apart from it handles geographic type points and can do geographic manipulation. And also when we come on to matplotlib, I'm going to assume you've got some basic knowledge of matplotlib there as well. Okay, so we're going to load up a map file, a shape file, which is going to draw regions. And the smallest region that we have in England and Wales is called a lower super output area. And here I have put a link. I'll check in a second that it's still working. But what you can normally do is use Google or whatever you normally use. And for example, here, lower super output area, often known as LSOAs. So I can just search for that, and I get a link. But here's where the fun starts with the government data, because let's have a look. Lower super output area, boundaries, that's good. Shape files, that's good. And there's clipped and full extent. I normally use the clipped. The full extent will just kind of draw, if you've got an island out that's part of the LSOA, like Lundy shares an LSOA with somewhere in North Devon or Somerset, I can't remember. It kind of draws a box up to include it, whereas the clipped is just a bit tidier. But if we click on full clipped, it's going to data.gov, and it says, sorry, it's not there anymore. This has been constant to all my time in trying to find geographic data sets from the government or the Office for National Statistics. Their links, so many of them are broken, and you just kind of get used to the pain of it. Can't find what you're looking for, so it gives us a search box. I did it before, lower super output areas. Now we're into a new page. What we've got LSOAs Wales, London, North East, East, South East, West Midlands, South West. But I'm looking for all of the UK, and there's one that's full extent. It's not clipped, but there's the clipped version. So if we click on that, it's going to show us here. This is quite nice. You know, if the original link pointed to this, you'd be fine. Sort of shows us what we're going to get. These are the regions. These are the LSOA regions, and then we can download that data set. And we want to download it as a shape file, is what we'll be using in Geopandas and QGIS as well. This, where you've got boundaries around a region, shape files are probably the most commonly used. But you see there are other formats. I think KML you use for Google Maps if you're doing it in that, but we're not. So you can download the whole data set there. Let's just check on this link that I've put in here to see whether that's actually going to work. Dun 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 dun. No, that doesn't work. I'll update that before you see this. By the time you see this, I'll make sure the link works today. It probably won't work tomorrow. Okay, so that's just what a shape file is, and what we often want to do is merge data, and what we will be doing is merge data with our shape file. And you can see there that you can download just the Southwest if you're working with the Southwest, but we're going to sort of manually select an area. But actually here, when we load up, we've loaded up a more restricted set, so just to save your bandwidth and computer a bit. So import modules, so standard stuff. So we're importing contextually Geopandas, matplotlib, and pandas there. So we can run that, or Shift Enter would do the same. Right, so now we're going to load up a shapefile, and this is where coordinate reference systems come in. And it is best if you know what coordinate reference system your geographic file is in, and if you specify it, then you're kind of on the safest ground. I happen to know, I mean, sometimes it's just a case of trying them, and then suddenly if you sort of plot somewhere you think should be in Devon or Cornwall, and it turns out to be somewhere close to the Azores when you produce the map, chances are it's your CRS is using the wrong system, and it's confusing lat long with British National Grid. So expect sometimes to need a bit of experimentation, but then you get used to the files that you're handling. So the file that we download from the government on the shape files, the lower super output area, that's in British National Grid, and that's EPSG 27700. Nice and catchy. So what this is going to do, this next line, we tell it the file name, and it's going to these shape files downloaded as a zip, and you keep them zipped. You don't need to unzip. And both QGIS and Geopandas will handle the zip, and the zip has various subfiles or various files in it that will handle. So we're going to load it up, and then we're going to use, instead of pandas read CSV, which you might have come across before, Geopandas read file. And what file are we going to read it? We're going to read it. We've given it our file name, where that is, and then we're going to set the CRS. And all of that's going to go into a GDF, geographic data frame, called LSOA. So let's just run that. And so here, this is where it's nice. It behaves just like pandas, in that I can say, well, show me the top 3 rows, and I can use lsjo gdf.head for 3. If you didn't have any numbers in there, it would give you default 5, I think. Let's see if I can make this a bit bigger as we go along. Okay, so what we've got, it's got an object ID, It's got an LSOA code, an LSOA name, and an LSOA name, I think that's, the W includes the Welsh names, I think. I tend to only use the LSOA name. The 11 is that it was produced in 2011. Presumably we'll get another set based on 2011 soonish. Sorry, 2021. If we're interested, we have the area of our LSOA in hectares and also the boundary. And this is the geographic information, and this is the polygon, and these are essentially the coordinates around the boundary that we're looking at. So this is how it creates the boundary with this series of coordinates. We don't need to worry about those, that's just how shapefiles work, and the format, and then Geopandas will handle all of that. Now we can produce a very simple map just by saying LSOA GDF.plot, and I'm going to give it a figure size here. The semicolon just suppresses any text output that it's going to give, so it's can be useful in Jupyter notebooks. If I don't do that, let's just run it again. I just get this axis subplot. It's alright, but it's not as, I think it's neater to have that suppressed. So that's our simple map, and you can see the region we've imported here. It's a fairly arbitrary cutoff. We're going to refine this, and so these are our coordinates. So these are eastings and these are northings compared to our standard reference point in the BNG system. So they are defined by the BNG, British National Grid Coordinate Reference System, otherwise known handily as EPSG 27700. Okay, so that's imported a shapefile, and if you're doing mapping, you'll use shapefiles quite a lot because they're the key ones for regions, and we can import our data, we can see our data, and we can plot it. Okay, so the next bit we're going to do is, we might be only interested in Devon or Cornwall, for example, out of all of this. So how do we select just one or more county to restrict our data to? And we're going to load another data set, and that data set, again, it's already there in your, if you downloaded the GitHub repo, and for all of the LSOAs, it tells us the county that it's in or the unitary authority, which we'll see in a second that you need. So, and it's a long file name, so this plus and then backslash is just dividing it up so it doesn't go too far across. But that creates a single file name with that bit added to that bit. Then we're going to read the file, and again this this time I'm going to set the CRS, slightly different way of doing it. So if you've got if you loaded up a data and then you want to tell Geopandas after you've loaded up the data what coordinate reference system it is, here I'm going to set it to British National Grid because I know that's what it's in. So let's look at that. So the full file name, you can just sort of see there, that's just what the plus, it just stops it all. We don't like very long lines in Python normally. Basically because you find a lot of the time you're spending cutting and pasting from one thing to another. So it's nice if you've got a Python file that fits in half of your screen, and without having to sort of scroll out to the right. So let's have a look at our counties. Oh, sorry, this isn't quite what it's not LSOAs for each. What this is going to give us is for each county We've got British National Grid, longitude and latitude. I imagine they are the centres. The area around the edge, so the area within it in hectares, and the area around. And then its geometry, it's got multi-polygon. Within that, it's got polygons which are they're the shape of an area, and it's giving a whole set of polygons that make up the Hartlepool region. So what we want to do is extract the Devon and Cornwall ones and say, for our map, check for each of the LSOAs, are you within the geometry of that county? So we can again have a quick look. So sort of unrefined but useful quick plots. We can just take our Geopandas data frame and plot, and this gives us a map of the counties. And so each county is a shape, a polygon. Polygons are just shapes. Right. At this point, if you haven't come across them yet, you're going to want to use, because it will make your life easier, Lambda functions. Lambda functions allow you to efficiently apply functions to pandas data frames, or in this case, Geopandas data frames. So please, at this point, pause and go across to this video. These are really great, I think. Socratica, they're a bit quirky, I like them. They're normally about, this is quite long, being 6 minutes. They're normally some sort of 3 to 5 minutes, and they just take one thing about Python and give you a nice explanation about it. So this is Lambda functions. They'll do it in pure Python, and then we'll apply them to a pandas data frame. So have a watch of that. Okay, you're all experts on Lambda functions now. And things like that. And as you sort of do more advanced stuff in Python, you'll come across maybe bits of Python you haven't used much before or at all. If you do that, if you can, spend a bit of time just trying some simple examples with stuff like Lambda functions. So we're going to apply the Lambda function to pull out whether a city name, which we're going to pull out of the county's GDF, or City Unity Authority 17 name, for each row, is it within the list of Devon, Cornwall, Plymouth or Torbay? So here's our Lambda function. We could have defined it separately, but we can do it directly here. We're applying that function to every row in a data frame with map. So map is a useful pandas method if you want to do something to every row. It's more efficient than writing something that iterates through the rows, which you could do. This kind of automatically iterates through the rows and does it in the most efficient way that it can. So let's have a look. Devon and Cornwall, we'll do that, and we'll have a look at that, and it will just be a bunch of trues or falses, or false or trues. And they all appear false at the moment. Sometimes you see that, but we can only see the beginning and the end. With Python, a true and false also has a value of 1 or 0, so we can sum those and just check. We should have found 4 rows, and we have, so that's good. Now we'll actually add that to our original data frame. I mean, when you've got data like this, there are various ways of handling it, but what we're going to do is, in our counties GDF, we're going to add that as a new column called Devon underscore Cornwall. And then if we look at what we've added, we have got this extra column down here. So this is all the counties in, was it England? Can't remember now. And whether it's true or false. And so it can be handy sometimes to collate data like that, and then you've got one data frame with things in. Now what I'm going to do is just select those columns, those rows, sorry, where Devon and Cornwall is true. So I'm going to create a mask. So our mask is counties Devon and Cornwall equals true. I mean, that will actually be another Boolean of trues and false. Then I'm going to apply that row-wise with .lock. And if I plot what, well, let's have a look. Before we plot it, let's just see what DC is. And DC now is our geographic data frame with our shapes, our multi-polygons, but this is now the whole data frame. I haven't used head, we've just got these 4 rows. And then we can plot that again with a simple method for checking as we go along. Okay, next section is on merging areas, because that can be quite handy at times to say, well, I've got this big polygon, I've got these 4 shape areas here. You can't really see, but there are Torbay boundary, Plymouth boundary, Devon and Cornwall. I want to create a one shape file for that. And I'm going to do it in a slightly more complicated way than I need to here, because I want to show you how you can merge in a data frame based on a value that's in a column. So you could be merging, rather than just saying, look, I've got all these 4 and I just want to merge them together. What I want to do is merge in a data frame based on whether you're in Devon and Cornwall or whether you're not. But that could be merging by any other characteristic in the data frame. And we're going to use what they call the dissolve method. And the dissolve method is merging areas, but you'll find in QGIS or wherever you're working, when you kind of combine areas, they call it dissolve. So I've got my merged data frame. I'm going to create a merged data frame, and that's going to be counties, counties data frame, geographic data frame, dot dissolve. What do I want to use to decide which group areas are going to go into? It's my Devon and Cornwall column there. So I do that. This will probably take about 30 seconds, so I'll pause the video. Okay, so now we can see what it's outputted is now we've got a data frame, Geopandas data frame, with just 2 rows. We've got Devon and Cornwall false, and it tells us it's got a multi-polygon, so it's defining lots of individual shapes. It keeps all of those in old shapes together, but in the polygon. And Devon and Cornwall true. If we look at, just pick out the true, if we sort of say show geometry, one of the nice things it happens in Jupyter notebooks is that it will show a map. What we're going to use this geometry for is we're going to select lower super output areas, LSOA, from our LSOA data frame, which you might have forgotten about. Back close to the beginning. And we're going to find those that belong to Devon and Cornwall. Now this is where we get into the geographic methods in Geopandas, and they're very powerful. Because it's going to it's not going to use any flag, are you in Devon or Cornwall or not. It's going to look at the geometry and say, is your geometry for an LSOA that, I don't know, might be in a little area of Exeter within Devon and Cornwall geometry. And there are a number of spatial relationships we can use, and I've linked here to a Wikipedia page on them. What we are going to do is if we just said I want to check all areas that are within, we find actually we miss some around the edges, and that's because they're not quite fully within. So we need ones that also kind of abut, or in our case, just to be safe, we'll use overlap. So we're looking for areas A that are within our Devon and Cornwall area B, or LSOAs that kind of straddle the boundary, in case they're not fully within. It could be that touches would be able to use as well, because it's abutted against the boundary. But I'm going to use overlap. So I'm going to use within. R is an LSOA within Devon and Cornwall, or does an LSOA kind of go over the boundary or touches the boundary of Devon and Cornwall? Now, because I've got two conditions I want to test, I want to use an OR. One of the slightly funny things about pandas in particular is that you do not type OR like you would in normal Python. You use a stick operator. Similarly, if you're using AND in pandas, you don't type AND, you use ampersand. And when I using the stick operator for OR, what I do is put each of the conditions wrapped in its own parentheses. So I've got, does an individual LSOA overlap, so is basically at the border, over the border of Devon and Cornwall, touching the border, or is the LSOA within Devon and Cornwall? So each of those conditions are in brackets, and then a stick OR operator in between. So let us run that. Okay, that took about a minute to do. Let's have a look at our mask. So now we've got a bunch of false and trues. So this applies to each of the original LSOAs and whether it is within our Devon and Cornwall geography. So we now apply that mask, we apply it row-wise with .lock. Sometimes you don't need the .lock, it's a bit, but if you are applying things row-wise, a Boolean mask row-wise, then .lock seems to be consistently reliable. So now if we look at our Devon and Cornwall LSOAs, then we're just looking at the top five rows, then all looks good. We can't tell it's absolutely worked at this point, but you know, we've got reasonable data there. But let's have a look at a map and see if we're convinced. And that's our Devon and Cornwall. So I think the first time I did this, it had two big holes where Torbay and Plymouth are, because I didn't take into account that they were they're not classed as Devon in that table because they're unitary authorities. Right, next section is, so far we've dealt with I'm just blinded a bit there. So far we've dealt with shape areas. Now we're going to add some point data. And we're going to load this in from a hospital CSV. It's got stroke information, so you could ignore all of that. It's got latitude and longitude in it. In fact, let's have a look. So I'm going to load it up into Hospitals GDF and have a look at that. Now I've used Geopandas read file, so it knows it's supposed to be a Geopandas file with geography. What we see when we look at it though, it's got lat and it's got long, so that's good, but they're not Geopandas geometry. And our geometry column, before we had polygon or multi-polygon, now it is empty. So it kind of knows it ought to have some geometry, but it hasn't got any. So what we need to do is set that geometry from our longitude and latitude. Now, you'll notice we've kind of flipped seamlessly, and it's easy to miss these things. That before we were dealing with British National Grid, eastings and northings. Now we're suddenly back in the world of longitude and latitude, because that's the information that's in this data frame. So that should ring bells, though often they don't to begin with, that actually we need to use a different coordinate reference system, CRS, for this, to set the geometry from the longitude and latitude. And what we're going to do is create longitude and latitude geometry and then set the appropriate coordinate reference system for this geometry. So the first one uses, we're going to say hospitals, this table geometry equals Geopandas, and then Geopandas has a method called points from XY, and we give it our longitude and then our latitude. Then we set what's the CRS for that geometry, and the CRS is WGS 84 is the reference system commonly known as, but it's also EPSG equals 4326 is how we tell Geopandas. Most of the time we're using one of three coordinate reference systems. So we've got British National Grid, which is EPSG 27700. We've got WGS 84, also known as EPSG 4326, which we've used here, which is the global lat long. And then there's a projection of lat long onto flat maps, which we'll use a bit later, which is EPSG 3857. And between those three, they're the ones we normally want to switch around with. If it's British National Grid, it is 27700. We use, if you're dealing with lat long data, it is 4326, until the time you want to make a flat map of it and bring in, for example, base maps, which we'll be doing in a bit, and then we use 3857. So it's just a bit of a recap there of the coordinate reference system. Those three are listed at the top of the notebook. So let's run that. Okay, now we've got our geometry, and we can see we've got our lat long fields still there, and our geometry has brought in longitude and latitude. But our other data is in the British National Grid system. And so what we want to do now is convert this geometry. We defined it based on lat long, so we had to say 4326. We're now going to change it to British National Grid geometry. So that's going to be eastings and northings. And we do 2 CRS, changes the geometry. So we're going to say change the geometry to 27700. It knows before it was 4326. Now we're going to change it. And so when we look at the geometry point, we've still got our lat long fields in, they're not changed. Our geometry now though, this top point, you can see the values are different, and we've gone from longitude to latitude and longitude and latitude to eastings and northings. And this is a bit fiddly to begin with, and you will run into problems occasionally with getting the right CRS at any particular point, and sometimes like this you have to load up one set of data with one CRS if one's lat long, another set of data with another CRF if it's British National Grid, and then we have to kind of convert them into the same thing. And then we'll have one more change later, which is when we want to apply a base map brought in with a system that's assuming we're using 3857. So let's plot this, and again, just with plot function, we can see we've got a very rudimentary map here with eastings and northings, and we can see our dots roughly in the shape of England, so that's quite good. Now we're going to use our geometry functions again. We're going to use within. What I want is just those hospitals where those points, and it knows where they are within our Devon and Cornwall geography, which was sorry for making me feel ill, scrolling up and down, I shouldn't do that. This is the area. So again, it's not using any labels, it's just saying it's your geometry within my defined area. Okay. And now I've got, this is the whole table now, I'm not using head, so I have just my 5 Devon and Cornwall hospitals here in its own table. So I'm going to want to plot those. I mean, we could just plot them again, but it won't be exciting at this point. Now I'm going to bring in travel times to closest hospital. Now we use a system called Routino which is a free system for getting travel times. It only works on Linux, I'm afraid, and it's all command line stuff and writing Python scripts for it. So it's not very user friendly. But at the top of this notebook, I've put a link which is travel times we've estimated, and they're sort of clear road travel times. Comes from OpenStreetMap, but then we calibrate against Google. They are travel times from all LSOAs, so there's 30,000 of them in the country, to 185 different acute hospitals. So I think we basically got every acute hospital in there. It's essentially any hospital with a labour ward, I think. But you'll find all, anything you think of as an acute or district hospital will be in there. But we're going to pull in just a fraction of that data. Again, there's stroke information in there, so don't worry about that. So this is part of the repository you downloaded, is we've got travel times. If we look at that, this is our LSOA, which is called area here. And the thing we're interested in is time to thrombolysis. And that's essentially, or time to thrombolysis unit is, think of that here as what's the travel time to my closest hospital. What we want to do is to pull that data in to our Devon and Cornwall LSOA. So we're going to add an extra column we want with travel time. And we're going to use the pandas merge merge method. And anybody who's done any SQL, I mean, you can look up more information. I'm not going to go into detail on merge. Have a look at the documentation. Very similar to SQL. We sort of say, well, we're merging this table, Devon and Cornwall, with travel time, and we're going to, our sort of lookup fields are our left table, which is the Devon and Cornwall. LSOA is called LSO11NM. In our right table, it's called area. And how is left means include all rows that are in Devon and Cornwall LSOA and bring in all the data you can for those, but don't merge in any data that's not, and LSOA is not in here. Now this, as it stands, will merge the whole two tables together, which can be sometimes is the easiest way to deal with things. But we could say, we could limit it and say we just want to merge on, well, we need area and we want time to thrombolysis unit. That should do it. Whoops. And then we can look at our merge data. We've got areas pulled in again. It's the same as 11 LSOA 11 name, and now we've got our timed thrombolysis unit. If you didn't have that bit in there, which is just restricting the columns we're going to pull in, it would pull in everything, which is fine. You can then select the data you want later, but I just thought I'd add that restriction in there. Okay, so we've got our hospitals. Let's show them on a map, and we're going to build up a map of travel times, our hospitals, and we're going to build a map with a base map. It's going to pull in a map from OpenStreetMap and apply that. So we'll build this up slowly. This does get a bit complicated, but the important thing here is have an example like this you can copy and paste and then adjust as you want. And I've tried to sort of put on appropriate comments here to help you see what they are. We're going to create, our figure is the overall matplotlib space. So I'm going to assume here you've got some basic knowledge of matplotlib. Our figure is our overall figure space, and our axe, we've got one is a set of axes within that. So we've got one chart within one overall area. And so we can define that with plot.subplots, and we say a maximum size of 10 by 10. Now our map's not likely to need to be square, but quite a handy thing is that we can give it the dimensions here, and it will create a map of the appropriate size without going larger than 10 inches in either direction. So now we use our plot function again, but we're going to give in some extra information. We're going to say the axes to apply is the matplotlib axes we defined here. Then when we say column to apply colour, it knows just column equals then timed thrombolysis unit. That is the column it knows that it's going to use to produce a gradiated map depending on the time to travel time. Anti-aliased is false. Something you have to sort of try some of these things and see whether on your map it improves or doesn't improve. But here it's going to avoid sort of artifactual boundary lines around LSOAs. The edge colour would normally be a fixed colour, so this is the area that it draws around the edge of the shape, the LSOA shape. We're going to say actually take it as the face colour, which it decides based on the time to the local hospital. Here we don't need to, but we can define our min-max on our legend, and that can be better to do it just because you can get slightly neater numbers used rather than it might choose while I'm going from 2 to 69 or something like that. So I'm going to say 0 and 70. So this is used for the colour scaling and for the key. The colour map, and just Google matplotlib colour maps and you'll see lots of nice images to quickly help you choose one. I'm going to use Inferno. So this is, do you want it just scaling from white to black or light blue to dark blue, green to red? These are all the different colour maps. Inferno's just nice and slightly dramatic. And then _R on almost all of the matplotlib colour maps, if not all, you can do _R to kind of reverse the direction the colour map goes in. So which is, if you're going from green to red, which is high and which is low. Use the same colour map but with R to reverse it if you want to have it moving in the other direction. Now, a slight disadvantage of this defining a maximum figure size is the legend thinks it's got all of that to go into. So it thinks, I've got 10 inches to fit my legend into. And so you can end up sometimes with, depending on how matplotlib then chooses to truncate things, it can make the legend appear much larger than the map. So sometimes you just have to have a go at shrinking it. So I've put just 0.5 here, and you can try just adjust that. And then I can give it a label, which is travel time minutes. So you'll see this is defined, hopefully you're beginning to recognise these things now, as a dictionary with keyword and value, keyword and value. Then I want to display the legend, and then that's all for that plot, but generally then I'm going to set the axes to be off. I don't want any coordinates on my x and y or axis points on there, and then I'm going to save the figure and show it. Let's have a look at this. So here's our map, just showing travel times at the moment. So Inferno's going from, or Inferno reversed is going from light through yellows and oranges, purples to dark. And we've got our legend here. So that's all nice. Next thing we're going to do is to add our hospitals to that and apply a base map. Now this, unfortunately, is where we need to switch to another coordinate reference system, and it's because convexity assumes that you are using 3857, the EPSG 3857, which is the most common projection for rendering maps to flat surfaces. So it takes lat long, or it's based on lat long, but then it projects in this slightly different way. So we're going to convert our data, not convert it, we're just going to say now, convert the geometry to assuming you're using 3857. So it will adjust the geometry points to do that. So run that. So I mean, the nice thing is you can easily flick between these different coordinate reference systems, and you can see it's instant to convert between one and another. Now, so this is our last map of the session, and it's quite long. You can see the code here, so it does look a bit scary to begin with, but let's go through it. The first bit is just the same as before. So this is mapping the travel time, creating the map exactly as before, including the legend. The only thing that is extra is transparency. I've set to 0.7. I can never remember whether this actually is transparency or opacity, whether 0 makes it completely transparent or completely opaque. I normally just have to have a play with those values. So this sets up the map and plots the travel time. Next we are going to plot the locations of the hospitals. This is just going to add the points. So we again use just the plot method, but then say we'll plot it on the axis I've defined for matplotlibplot. The edge colour of my symbols will be black. I don't know why matplotlib use K for black. Face colour white, marker size 200, and use stars as the marker. The next one is the most fiddly, I think, but again you just copy and paste and adjust accordingly. This is adding the labels, and it's going to create its own zip, which is sort of combining two kind of lists, if you like, into something it can then also iterate through itself. And we pass in the hospital geometry, the X point and the Y point, and then its actual hospital, and then we're going to annotate, which is create the label, and we create our label. So this is the hospital name here, which we've defined. This label here came from DC hospital here, and we say what's the X and Y? Well, it's the X and Y because that's what we've called them up here. And then XY text is 8.8, 8,8, but then we define what we mean by that, and we say the text coordinates that we've given are offset points. So this is the distance right and up from the main point. So if you had 0, 0, or presumably if you didn't pass this argument in, it would start labelling bang on the centre of the point. Background colour for the text is white, and we can change the font size. So that's a bit fiddly, but so you cut and paste. You don't try and remember these sort of things, or at least I don't. Then we're going to add a base map, and this is really beautifully simple. This is, we imported contextually earlier, CTX earlier, and we use its method add base map. Where do you want to add the base map to? Add it onto the axes. It knows what you're trying to map, so it will then just go and get the appropriate, what's called mapping tiles, from OpenStreetMap, Mapnik. So that's its source. If you Google contextually sources, you'll come up with all sorts. They're sort of fascinating. You know, you can bring in a background map which is all railways or something like that. There are loads of them, or there are ones for the sea as well as the land. But we're going to use OpenStreetMap. Zoom we probably don't need. This might do it automatically, but this is the level, basically the level of detail that it's going to show, because OpenStreetMap, as you kind of zoom in, you can go down to sort of houses, see individual houses as symbols, blocks, and then as you zoom out you just see main roads and town names and that. So you probably don't need that, but I have set this here, and you can change that and see what it does. So that's adding the base map. Then we turn the axis off. So this is, don't plot what the latitude and longitude are. Don't add little grids or axes lines on, and add a title, travel time to closest acute stroke unit in this case. Now this bit is, I think it ought to be not needed, and maybe with later versions or maybe even current versions. What I found is that it sometimes saves a map with too large margins around. So this allows you to adjust things and just make it nice and tight on the image it saves. So if you need to, put that in, try these as defaults, and then adjust if it's losing some of the map, or you've got too much space on one side of the map or above or below the map, and then we'll save it. And I'm just running that. And there we are. So we have our travel times, we have our base map, and some transparency. We could want to adjust that, but you can sort of see the roads coming through here, you can on my screen. And then our hospital names, which in my table is just their postcode. That's just what I call the hospitals in that table. And then we've saved that. And then you see it's, because of this standard format, you can very easily then automate generation of maps and bring in different tables with different results and produce them and save them. That's it for the main session. The only other thing I'll quickly show you is what's in the second notebook, but we won't go through it. It's all basically the same kind of stuff, but the second notebook, the difference is it takes you, if you want to produce an inset map, then you can produce an inset map, here the Isles of Scilly, alongside a main Devon and Cornwall. So have a go with that if you want to. It's all exactly before. It's just it really is just the matplotlib functions to say we've got two axes now, one for the main one for the small one, and how in matplotlib you show both of those, and you can bring in base maps for both again. Right, that's it. So have fun. These are very powerful systems, very fiddly, a bit fiddly to begin with, but once you get used to them and then have your own bits of code that you copy and paste, it's very good. Between this and QGIS, they're wonderful resources to have. Okay, goodbye world.